отпечатки пальцев уже, ну невозможно.
Я понимаю, а как это сейчас? А как это используется?
Ну это Бог позвонит туда, спросил, поговорил.
А куда им нам позвонить, ты можешь?
Ну в это паспортное.
А можно, чтобы какая-то была?
Ну я же тебе присылал все. Я же тебе присылал, читайте. Да. Да.
Хорошо. А можешь попросить если наши няни звонит, тогда там точно делать.
Да, могу. Только не сейчас. Сейчас не нравится.
Конечно, не сейчас.
Угу, конечно.
Ладно, хорошо, спасибо.
Okay. So I'm sorry for missed lectures. Let me make a brief review what we studied up to now. Up to now we studied the language. It was one thing. Second, we studied examples of topological theories. And then the main question is how this one is related to these two. So the goal of today's talk is to relate 1 and 2. Okay? Before I do this, I want to say a little bit more about topological theory. Because, as you will see, it will be helpful. So first is the topological quantum mechanics. So I used to call it higher topological quantum mechanics. But when I mean topological quantum mechanics, I mean that Hamiltonian is anti-commutator of Q and G such that Q squares to 0. And let me also assume that G also. So what do we know about this theory? We can consider what is called partition function. Supertrace e to the minus th. And this partition function is actually an invariant. First, does not depend on P. It explains why it's called topological. Depends only on the fact that we have a circle in time. That's why it's topological. Second, if I change Hamiltonian plus delta Hamiltonian such that delta Hamiltonian is U of something, the result is not changing. Actually, it's because you may check that it is an index. Okay, so it's an easy state. But this is about partition function. The next important objects are correlated. So what are correlators on a circle? By the way, supertrace means that you take trace over even space with a plus and over odd space with a minus. Parity. So correlator on the circle. So let me take 2 points. For example, I can take n points, but the formula would be too long. Let this time be t1, let this time be t2. Let me assign to this point phi1 and to this point phi2. And let me further assume that q phi1, q phi I commutator equals to 0. Then such correlator that I symbolically depict as this is supertrace e to the minus t2a. Phi1 e to the minus t1 h phi2. What is important is that this correlator has the following properties. Property A. If phi I is changed by phi I plus q of psi I, this correlator is not changing. Why? Let me plug this gadget here. I will get q of psi. Then I'm taking q all the way around, and I'm getting 0. Property B. Correlator does not depend on T1 and T2, namely on positions of the point. So how can we check it? There are 2 ways to check it. First way is take derivative with respect to T1. We will get H downstairs. And then H is Q of G. And we will use the same argument. However, there is even better argument. Better argument is better because it could be applied to higher dimensional theories. It's prototype of the argument in higher dimensional theories. You may consider this as a correlator of the circle with the length T1 plus T2 and you put phi1 at time T1, phi2 at time T2. And then you may change, and here I'm using so-called Heisenberg representation in quantum mechanics. So in Heisenberg representation, phi of t is e to the th phi e to the minus. And then from Heisenberg representation, I will see that d phi over dt is what? Is h phi. Now, since h is q of g, I deduce that d phi over dt is commutator of q of g. And this property is kind of important. Let me even put it on the special board. It says that d phi over dt is u of g of phi. Let me tell you why it's important. This is linear algebra. And on this linear algebra, you can honestly compute everything. In the case of higher dimensional quantum field theory, you may assume that you will have phi 1 of x1, etc., phi n, etc. You may assume that q of phi I equals 0. And then you may imagine that this correlator is topological. Topological because theory is topological, so it does not depend on the example. So how does it happen? First, if phi I is q of psi I, then we assume that q is a symmetry, that this correlator vanishes. Therefore, this independence may be related to the following fact, that d phi I as an operator is actually u of some other psi. Tilde. So people call this phi I1. And this relation is known as Edwards-Witten descent. So these are the general properties of topological theories that we assume to have. Okay?
Excuse me, can you explain the second line?
So,
I mean the property 2.
property 2 means that if we take v with respect to x, this should be 0. Now, what does it mean? It means that at the ith point, we have observable vxi. And then we may ask, why such correlator vanishes? And the good guess is that it vanishes for all other phi's. That it vanishes because it's Q of something else.
So it's an assumption.
It's an assumption, yes. In the case of quantum mechanics, we kind of proved it. But this is a general case. Actually, to tell the truth, this assumption could be proved from the fact that energy momentum tensor is Q G. But now I'm not going to talk about it. So, what I did right now, I reminded you the basic facts about topological TFT. So we had examples of topological TFT. And so now we add basic facts. So what is important? Important is independence on the position. It's one important thing. And the second important thing is that if we modify, say, H as a Q of something, the answer is independent. So it is in the case of quantum mechanics, and in the case of higher dimensional topological theories, I just want to tell you that there are deformations of the theory that lead to equivalent theories. Okay. Now I want to go to BB language, because it turns out that BB language somehow encodes this property in a very non-trivial way. But before I go to the BB language, I would like to review some basic facts from symplectic geometry. If we have a space with symplectic form the half-dimensional space is called Lagrangian. We call it if omega restricted to L equals to 0. Suppose we have Darboux coordinates phi I and phi star I. Then there are Lagrangian submanifolds that could be projected to phi. Such Lagrangian submanifolds are described by so-called F that depends only on phi i's. By equation, let us check that it is actually a Lagrangian submanifold. So let us compute this option. Now we have symmetry here and anti-symmetry here. So that's why result is 0. Second, there are different diffeomorphisms of the symplectic space. However, there are canonical transformations. So canonical transformations are diffeomorphisms of symplectic space that preserve omega. All these canonical transformations by functions on symplectic. That I'll call R. And infinitesimal infinitesimal canonical transformations are generated by functions on symplectic space that I call R. How do they act? You may write two formulas. Formula A. R acts as following. It takes functions into functions plus R function. Over here we have a bracket with respect to symplectic, with respect to Poisson bivector associated to symplectic form. So it means that the vector field is pi ij dr over dxj. Now, the good question is why these vector fields preserve omega. Let us rewrite this formula in the following way. IV, so I take this pi to the left hand side, and I have IV applied to omega equals dr. So this is a one form, omega is a two form, and here I have contraction with the vector. Now I'd apply the rank differential to both sides. since d squares to 0. Here I commute d and iv to get lv. So from this I conclude that lv omega plus iv d omega equals to 0. Now, or minus, doesn't matter. Now d omega equals to 0 because it's a definition of symplectic form. So I conclude that such diffeomorphisms preserve symplectic form. Okay, so this is so this is the piece from symplectic geometry that I wanted to tell, or to remind you. Now let us come to the interesting stuff. At the moment, everything is separated. Topological theories were one thing, BV language with Lagrangian submanifold was some other thing. It was absolutely unclear how they are related. And now we will come to these relations. I'm going to prove important theorem. And this important theorem is like this. Let S be a solution quantum master equation I would even like to assume as a stronger form. For simplicity. Consider dv integral. So here L, say, is given by equations that I described. Phi star I is df over d phi I. Let me call it I. So now the theorem is that I is independent on the choice of L. Why? We can anticipate this theorem. We can anticipate this theorem because this else actually came from the cycle. Under old Fourier transform. And homotopy cycle probably would give equivalent Lagrangians. But we need a stronger version of this theorem. So, how should we proceed? We should proceed by definition. We have an integral over d phi e that depends on s, that depends on phi I, and it also depends on df over d phi I. So it's I. So what is the variation? Things come from exponent. And here I need to write variation of s. Now I can rearrange this term as ds over d phi star, because I need to take variation of this term. And here I have df over d phi I. Sorry, not df, d delta. And then I will use the following trick. I will integrate by parts. So I take this derivative and I apply it to the left. So what would I get? I will get several terms. First of all, this derivative can hit here. Okay? When this derivative hits here, I'm getting Mirila pressure in OS. But I assume that it is zero. This derivative could hit here. Okay? If it hits here, I will get the following structure. T to S over d phi I, d phi j. D to F over d phi I, d phi j. Sorry, stars here. But now stars have opposite statistics in comparison with non-stars. That's why this term goes away. Now I have an extra piece. This derivative could hit the exponent itself. And again I have two pieces. Piece So piece when I hit here would bring me ds over d phi I ds over d phi I star. But this is the classical piece of the master equation. Okay, hope assignment. Complete this consideration by yourself. I gave you the idea how to compute and why the result is expected to be zero. So there was this very heuristic argument and very incomplete. And here there is something more solid. So immediate corollary. How to prove it? I take R as a generator of canonical transformation. And using the diff invariance of the construction, this equals to integral over L R transform. And we already checked that if we make transformation of Lagrangian submanifold, the answer is independent. Now, we see that BV integral really has the properties of topological quantum field theory. It contains this kind of symmetry. And you may change S by S of R, and the answer is independent. And you may also do the following, differentiating by epsilon. You may prove that this is 0. So this BV bracket with S plays the role of Q in topological quantum field theory. And finally, after weeks of preparation, I'm able to make connection between BV language and topological field theory. Okay, so it is a very good moment to make a break. You need to think about it, yes. And after the break, we would consider examples. Because theory without examples is empty. That's we with Slava believe. And as always, we would start at 16:30. So somehow it happens that we always start at 16:30. So now we will have only 10 minutes break.
这里 R 是什么？有人也说了，generator 我们看了，它是一种
那个 syntax form 的，
对，它是那个什么东西啊？就是比如说有个 symplectic 那个是什么 symplectic homomorphism，然后它是一个 isomorphism， 一种 isomorphism， 它是一种对应，然后它有 generator R 是 generator， 所以它是一个我这里它是那个它是个什么对象？就是现在是为什么它能跟这个 S 做什么 bracket？ 这个 R 就是长成这个样子。在 local 上它长什么样？比如说我们现在用phi star 做这个实现嘛，对吧？然后你一个 symplectic transformation， 或者你 canonical， 不然这个 R 叫什么 canonical transformation 应该长什么样？为什么它能够 做这个 bracket。
它这个讲的是什么意象？是一种 partial，
就是你，就是你的所有的那个，就是这个 R 对吧？对，就是这个 F 是那个 function or symplectic space。对，就是你有一个 given algorithm，你就有一个类似于一个，就是所有的 given algorithm放在一块儿，它可以构成一个 group。对。然后 R 就它的 algebra。
就比如是 translation， 就是 F 变成 F 加 A， 那个这 R 就是对，是这个意思。
啊，这个 R 应该是 A 倍的 partial，
对
partial x。对。它 logo 上写的。
什么意思？我这个记号什么意思？
就是这个算术作用程序。
对，就这个，首先你有 space of given algorithm plus D group， 然后有 D group 就有 algebra。R 就是这个 D group 和元素对应的 algebra。OK。因为 algebra 就很在上面，它长这个样子，后面这个东西是它的改变的部分。然后你 logo 上来写的话，这个 R 取决于你这个 diffeomorphism 长什么样子。比如说，如果你这个 diffeomorphism 是 translation，
就是这个记号其实没有
它这个 general 你写不出来 logo。
这个记号是什么意思？让我思考，因为你这个 bracket 有名字吗？还是只是一个记号？
它在它这里应该就是特征 BV bracket。
这是 BV bracket。
我觉得应该是 BV。我觉得应该是 BV bracket， 但是
那所以 R 应该能写出来它长什么样子是吧？
对，应该能写出来了。但是没有，你的 R 不取，你 R 在这个 BV bracket 下呈现出来可以写出来，但是你这一块这个整体的结果，比如说你考虑 translation， 你可以知道的是，如果 R 是 translation， 就是 P1的，你可以知道它是这样的样子，对于一维是这样。但是它不一定是它有可能，它应该还是这样子。
OK， 你现在这个作用知道什么？那所以 R 应该本身也是可以写出来它长什么样子。然后就因为这个 bracket 和 BV bracket 也具体的。
对，就这个东西可以写成 BV bracket 的形式，可以写是比如说 AP 加 BX， 把这个带进去就这个东西，因为你 BV 是这个，我假设所有都是 O 的，然后你一个放这儿，一个放这儿，一个放这儿，刚好对上这个，所以
R 是
所以这个可以写成 BV 的形式。
那对于新的这个 symplectic morphism， 它大概是长什么样？
所以这也是个函数。
对，
它也是用。
在我这里写的也是函数，那更一般的应该是个 operator， 那应该是个方形，它应该是个方形，对，应该是个方形，是函数。
你在这个具体的例子里面应该是长什么？
就是写不出来，R 是随便一个就是553的函数，然后你和 F 作用一下，相当于是可以写出来一个写出来一个对像 bottom bracket 或者 B bracket， 你这个结构给出来以后，这就是一个具体的一个代数运算，两个函数作用出来一个函数，把这个函数。
但是你相对于就是你这个 R 是指定了，它说是那个 symplectic transform， 它应该相对于一般的应该有些限制。
它应该是对于一个 R， 它是这样的，对于一个这样的 R， 你做一个这样的 infinitesimal 的 transformation， 你可以倒推出来，跟这个 R 有关有一个地方，它这个东西。
你的意思是这个 diffeomorphism 不一定是一个 preserve symplectic form， 但是如果它这个它已经含有这个 symplectic form 的信息了，所以感觉是匹配的，应该 consistent， 就是它这里摆的已经是这个 symplectic form 做出来的 bottom bracket， 所以这个写出来应该意思就是它自然的保持这个，也就是说像这种东西，它就是一个无限小的 symplectic form 的象征，对，它的 act 在这个 F 上，它会得到一个什么？这个保持的这个 symplectic form。
我认识。 是 SS 对它有点加起来，对对，所以它是以这个 special case。那你看它推导，它最后出来全部都是 SS 这是 SS。啊，这个。
So now we will go to examples. And let me start with the simplest examples. And simplest examples are, of course, in dimension 0. So what is the field theory in dimension 0? It's just ordinary integral. Suppose we have a space X with coordinates x nu. And suppose we have a function f. Let me do the following. Let me consider space Ptx is the same as P1 of x, such that functions on this ETX are differential forms on it. So they are just functions omega on x, mu, and psi. Now I want to construct the following DV space. It is PT star to PTX times PT star to PP of some space C. So this looks as something complicated, however, it's not that complicated. Coordinates here are x mu and psi mu. Coordinates here are x star mu, psi star mu. Okay, the second factor. Coordinates here are write it the following way. T, C. Coordinates here are pi and p. So these are even, this is odd. This is even, this is odd. I want this to be odd, and I want this to be even. And then I would also like to have pi star. That would be even, and p star, that would be odd. Now, I would like to write down action. Action would be quite simple, and it would solve dV. Namely, it would be psi mu x mu star plus p star pi star p. You may easily check that this S solves master equation, classical master equation, quantum master equation. Now, let me take Lagrangian submanifold. And as a Lagrangian submanifold, I need to find a generating function. And I would like to take this generating function So generating function is a function of the fields only. So it depends. It should depend on x psi p and phi. But I will take very special function. Namely, I will take my function f that depends only on x. And I will multiply it by p. Very simple function. So you should not be frightened by the number of variables, because example is really simple. Now I need to express anti-fields, these with stars, in terms of fields to go to Lagrangian submanifold. In particular, phi star should be df over d pi, and it is easy, it is f of x. X star, it's more interesting. It is df with respect to dx mu. So this is df of x over dx mu. And that's it, because we have no other anti-fields in the action. So what kind of action do we get? I think I forgot here pi. Of course I forgot pi. So this is our good old friend. It's Mathai equivalent action. Now we have this interesting symmetry. H goes into H plus S and H. So what does this symmetry mean? H depends only on x and psi. It is a differential. X and H is just the rank of the space X of H. If H depends also on phi and p, then S of H is this very interesting object, d over d pi. And we already studied it in the case of mosaic wheeling in the following picture. Here we have X with the even coordinates. Here we have space with the odd coordinates by. And this object is at the round differential here. So that's how it works. So it's not that hard. It's not that terrible. Before we go further, I need to remind you, I thought I explained it to you before, but I need to remind you what is BRST procedure in gauge theory. In the textbooks, so I don't know which textbooks are you using, but if you're taking course on gauge theory, you will find an explanation of the following fact, that if you have a theory S of phi with a gauge symmetry V of phi, then you can make a gauge fixing. So what is gauge fixing in the textbooks? You introduce costs CA corresponding to the vector fields and cost B alpha corresponding to gauge fixing. That I unfortunately call with the same letter F alpha. You also introduce Lagrange multiplier. Okay, I will write and then action go gauge fixed equals S of phi plus you have H alpha F alpha plus you have term where ghosts C and B. Enter. And this term is the following. LVA applied to functions f alpha VA. Maybe it's better to write. And this is called B-restrict gauge fixing. Okay, it's called gauge fixing. Now I'd like to give this gauge fixing interpretation in terms of BV action and Lagrangian submanifold. I will have BV action with the fields phi and anti-fields phi star, with the fields CA and anti-field CA star. You may think, look, no B field is entering the business. How strange. It's not that strange. The BV action here is plus structure constant of the Lie algebra. Now, this is gauge fixed. Now I'm doing BV construction. And my goal is to show that BV construction gives the same as the gauge fixed approach. Now, I am going to do the following. I am going to take Lagrangian submanifold. Now it will be not Lagrangian submanifold that projects on the phi fields. It will be different, topologically different. But this Lagrangian submanifold would correspond to the so-called conormal bundle. So we impose condition F small equals to 0 when we impose these conditions. We have the phenomena that we studied. That when you restrict in directions of phi, you have a freedom to go in phi star direction. So actually, if you restrict it like this, then you have a freedom to go to phi star, and phi star I could be actually written as BF alpha over D I or mu Q. B alpha. So would phi be even, these B's would be odd. Now let us check that it is Lagrangian submanifold. Delta phi it's what? So here we have delta phi I. And here we have delta phi I star. But it is not arbitrary, it's this. D2F alpha. Sorry, not IJ. Okay, IJ, I. So here I have I. D2F alpha over D phi I over D phi J delta phi J. But now once again, we have this argument. This object is symmetric, this object is antisymmetric, that's why it's 0. So that's why this L is actually Lagrangian submanifold. Maybe I'm going too fast, so if I'm not going too fast, I will do the following. I will restrict myself to Lagrangian submanifold. I plug it here. And this L would bring me CA, VA, I, VF alpha over D phi I, B alpha. Exactly the Gauss term in gauge fixing procedure. Of course, I assume that C star will be 0 in this Lagrangian submanifold. And now, what about this term? This term is needed to impose the condition that f alpha on phi equals 0. So that's why gauge fixed procedure and DV procedure are equivalent. You see, in this way, so what I'm doing in this way, I'm increasing the number of examples. And I will increase the number of examples until we would be able to derive AKSZ, going from simpler example to more and more complicated examples. So this is my plan. So would I bring you this AKSZ construction, you would say it is abstract formality and you would not know how to do with it. But I decided to take a path based on examples and increasing complication of examples. Okay, so all this works in any number of dimensions, and particularly in dimension equals 0. Let me go to higher dimensions. So would our colleague Slava be here? He would say that the next step would be to go to dimension 1. But I don't want to go to dimension 1, because in dimension 1 you will meet so-called gauge quantum mechanics, and you are not familiar with it. So that's why I skip dimension 1 and land to a theory that you probably would feel more standard. It's called D equals 2 G0 squared equals to 0 Young Mills. That we studied as a reduction of Chern-Simons theory. So before I made kind of review of what kind of topological theories could we have. And we had this theory. And let me first consider abelian case. You may think that abelian case is almost an empty theory. So let me remind you that in non-abelian case, the action was like this. Where phi was a function, matrix have its function. And A is a matrix valued one. Actually, it's a connection, but I don't want to go into this mathematical detail. And let me study abelian case first. In abelian case, such term is absent. So theory is very simple. But I took my path to go from simple cases to more complicated cases. And finally, we would land into AKSZ theory. So this theory is simple. This theory has a symmetry. A is going to A plus B epsilon. So, how can we write it? Let us write it in the gauge fixed form. I want you to see that that what we are doing is kind of a standard thing, not a new procedure. So what could be the gauge fixing? So this is the Hodge star. So if you don't remember what the Hodge star means, let me remind you that this star on A on X side is D over D X mu D over D psi mu G mu, where G mu is the metric on it. On X2, two-dimensional space. So if we impose such condition, this is no longer a symmetry. Now we have interesting time trying to understand this CV phi term.
Excuse me, what do you mean by post this condition?
So it's equation on A. We want to impose this equation to fix this symmetry. based on compact manifold.
Equation and f, there should be an equal.
Yes, equation is this equals to, so function equals d star a, and condition f alpha equals to 0 is this condition. So what is this Faddeev-Popov term? CV 5 star. It's a kind of standard term in the business and this is this. So let me try to explain this formula. So first of all, this function is linear in A. So we just write it as linear in A. Probably I need to rewrite it in another way. So it's linear in A. Now we need to apply to this function vector field. So what does it mean to apply to this function a vector field? It means to replace A by BC. Oh, I'm sorry. I wrote it in a different way. So what is this? A goes to A plus BC. D star A goes to D star A plus D star BC. So that's what is written here. I need to take this transformation and act by it on the function f. And I need to multiply by the field.
Shouldn't there be the minus sign because of
Probably.
rotation C and
You see, it's up to minus signs. You see, I don't remember signs. I'm sorry. Okay, and now we may add or we may not add the Lagrangian multiply. So this is something that all physicists would write here. Now there is an interesting trick that I would like to do. I would like to say so let us, as above, let us forget about H and just assume that B star A equals to 0. Now, interesting phenomena. I would like to take this B star and act on B. And what would I say? So this is one form. This is also be a one form. I would like to say that here I have B star exact B. And here I am making a trick. I would say, look, B star exact B is exactly the field phi 1 with condition B star phi 1 equals 2. So I will rewrite this action as trace phi dA plus, okay, no, trace and ability. Phi 1 dt with an extra condition. dA with the star equals to 0. D star phi 1 also equals to 0. Now I can say, look, I have 4 fields here. 2 one forms and 2 scalars. D star on scalar equals to 0. Because D star lowers the degree of the differential form. So actually, I found here this magic formula. It looks that everything is composed out of superfields where one of the superfields contains of phi and phi 1 and another superfield contains of A and C. In the old literature it was called Russian formula, uniting A and C in one object. And this is the story. I forgot to tell you. One can check that this is actually Lagrangian submatrix. If I consider phi being A star, So now I will erase this story about watch star, and I would like to say, okay, my new field is A plus C, and I call it calligraphic A. I have another field that is calligraphic phi. And that I'd like to understand as A star. And I'd like to form BV symplectic form between that. And now, if I impose these conditions, that it is actually Lagrangian submanifold in this symplectic form. And here we are coming very close to AKSZ formulation of topological field theories. Because our next step, so let me see, let me check the time. Okay, I have some time. Our next step would be to consider non-abelian analog. So if abelian case is clear, so I give you some time to evaluate abelian case. So the main formula in abelian case is that S is actually a calligraphic star D A. Where A calligraphic is A, that is a one form, and C, that is a zero form, and phi calligraphic is phi, that is a zero form, and phi 1, that is a one form. And parity of these fields are opposite. So this is simplest AKSZ. Together with the Lagrangian submanifold, B star of A calligraphic equals B star of A equals to 0. You may ask why it is Lagrangian. It is because if I have D star exact here, I can put it on the second part, and I will get 0 since D star squares to 0. So this is really simple. Now let us try to generalize it to get AKSZ. We need to start with this, trying to generalize it. Now we have to verify dA plus A squared plus we have again D star B D plus A acting on C. So this is the gauge transformation of the field A. Okay, so here is commuting.
And DC is completed.
And what?
DC plus completed.
Yes, DC plus commutation. So here we need to look only at terms that do not contain this derivative. But they are pretty simple. Here we have extra terms. Phi A squared and B star B AC. Here we have this. We will do the same trick. Understand it as phi 1. And check that what we have here is actually integral of A star dA, it's an old term, plus a new term, A star A squared. So if A star is a function, we have A squared term. If A star is phi 1, from here we get commutator of A and C. And this is also AKSZ. Now, if I'll write it in components and not in terms of matrices, I will express it as A star A, D, A calligraphic A plus F A B C A B A C. And it solves master equation. But now I can make a new generalization. And generalization is that I may generalize this formula to AA star BAA plus FA A1 AK A curly A1 A curly AK. And I may ask when this solves master equation. And it solves master equation exactly when these f's are structured quantum of L infinity L2.
Is there some of k?
What?
Is there some over k?
Yes. And in particular, okay, so here I assume that A can be either even or odd. So when we started from gauge theory, A was connection. Its coefficients were even. But here we are going to generalization. And here we are almost at AKSZ. So what do we need to add to get AKSZ? We need the following. We need to add differential FA1, just like we had in a zero-dimensional sum. Moreover, okay, now I'll say in words, okay? To get AKSZ, we need to say, look, we have the following structures. A star dA is kind of universal structure. Plus A star, and here we have what is called homological vector field. This could be generalized to some functions of A star and A. Solving master equation. And this is already AKSZ. Okay? And I'd like to stop here. So, summarizing today's lecture, we recalled I want to say one thing in the end. Remember, we had terms that decoupled. So in the absence okay, no, I don't want to say everything today. It's too late. once again, summarizing. I started by recalling properties of topological theory. Then I recalled something from symplectic geometry. Then, interestingly enough, this odd symplectic geometry has the properties similar to properties that we expect from topological theories. And what did we get? We started with a theory that looked like topological, two-dimensional Young-Mills, and we discussed why it's topological from BRST approach. It's because its action was topological and the rest term was gauge fixing. And we reformulated it in a very interesting and promising language. And this is the language of AKSZ that allows generalization, that allows various generalization. Yes, so now I want to finish. Okay.